So here I want to start with actually the mechanism that enables neurons to generate electricity. Because as I said, you saw that there are these electrical signals in neurons, but what makes it possible? Why do they generate electrical activity? So here is a schematic draft or drawing of a neuron. Of course, a neuron is not a circle. You saw that it has this structure, but let's look at it as it is. So this blue circle is supposed to represent the membrane of the neuron, enclosure of the neuron. There is a membrane, and there is the outside of the neuron and the inside of the neuron here, inside the membrane, and there is the outside of the neuron here. And between the outside of the neuron and the inside of the neuron, there are this ion concentration. Okay, so there are three ions, key ions, that carry charge across the membrane of the neuron. There are the sodium ions, the potassium ions, and the chloride ions. And these three ions have different concentration between the outside and the inside of the membrane. And these different concentrations, as you will see soon, can go through, or the ions can flow through membrane ion channels, which are particular proteins that might enable, when they're open, these channels, can enable the flow of ion, let's say from the outside to the inside or from the inside to the outside, depending on the concentration gradients across the membrane. So here are really typical numbers. So let's look at the sodium ion. You can see that on the outside it is highly concentrated compared to the inside. So if I will now open a channel for the sodium, the direction of flow will be from the outside into the inside. In the case of potassium, you see it's highly concentrated in the inside and less concentrated on the outside. So if I will open a specific ion channel to potassium, the current flow from inside to outside. And so is the case for chloride. It's highly concentrated in the outside. It's much less concentrated in the inside. And this will enable chloride to flow from the outside to the inside in case a chloride channel will be open. So this channel that you see here schematically is specific. It is embedded in the membrane of neurons. And when open, this specific ion channel, let's say for chloride, if this channel is open, then chloride will start to flow from the outside into the inside. And if it's, let's say, sodium channel, it will do the same. If this channel is a specific sodium channel, then the sodium will flow from the outside to the inside. And if it would have been potassium channel, the current will flow through the channel from the inside to the outside. So that's really what causes the membrane of neurons to be charged, because these ions are charged and they have a tendency to flow from one direction, from in to out or from out to in, depending on this gradient of concentrations. And the only question is which ion or which channels will enable which ion to flow. So if the membrane is completely sealed, no current will flow. And if there are channels open, current will start to flow. And when I say current, I mean either sodium current or potassium current or chloride current. These are the three currents that enable the neuron to become an electrical device. So in order to develop an understanding about what is really making these gradients of ions behave like an electrical device, there is the very well-known Nernst equation here, which really describes what is the battery, so to speak, what is the driving force of these ions as a function of the concentration difference between the outside of the membrane of particular ion to the inside. So this is the concentration of the ion, let's say potassium, in the outside or potassium in the inside. And this, according to the Nernst equation, these gradients with some constants here that you can see defined in this case here. These numbers, these constants, will give you voltage here. So this is battery in units of volts or millivolts. And the value of this battery depends on the gradients of ions from the inside and the outside of the membrane, and on these constants, which is, by the way, this constants is around 60 millivolt here. And Z is the charge of this particular ion. Okay, so now let's look at this Nernst equation for each ion. So the Nernst equation describes the, so to speak, battery, this battery for a particular ion. Let's look at the battery of the sodium, because the sodium is highly concentrated on the outside and it's less concentrated in the inside. You'll do this Nernst equation computation and you will see that you will get a number of plus 60 millivolt. This means that because sodium tends to flow from outside to inside, it tends to charge the inside of the neuron with positive charge to the level of plus 60 millivolts inside the cell. The potassium, and I can see here that there is a mistake if you compare it to the left. So the potassium is actually less concentrated in the outside and more concentrated in the inside. It's molar here, molar here. So there is a tendency, as we saw here in the left, of the potassium to go to flow, if possible. If there is a channel open, it will flow from inside to the outside, and this will leave a negative trace inside. You lose positive charge when a potassium flows from inside to outside, and this will give you a battery here of negative charge inside the cell. So the battery of the potassium is about minus 72 inside of the cell compared to the outside. And here you see the chloride, and this is the battery of the chloride, minus almost 90 millivolts inside of the neuron. So these are the three basic ions that generate electrical activity in neurons. And in the case as it is with the concentration using the Nernst equation, you can see the battery for each one separated on their own. But of course they are not on their own, because all the three of them appear together in the neuron outside and inside, as we can see in the left. So we actually have to find a way to describe the combined voltage or the combined battery of all the three together. So in order to do that, in order to understand how does one do that, I'm going back to the same description. So there is this schematic neuron, this spherical or this circular neuron, the inside of the neuron here, the outside of the neuron there. There is this channel or channels that enable sodium, potassium, or chloride to flow from the inside to the outside. And I define now the voltage across the membrane as the difference between the voltage outside of the membrane to the voltage inside of the membrane. So I define now V membrane here as the difference between V in minus V out. So the difference between the voltage inside the cell to the voltage outside of the cell. Okay, and here I want to write down for the first time in this course the electrical equivalent circuit for what I just described until now. So how do I describe now a channel electrically? So we saw that a channel is like a conductor. When open, it can conduct ions through the channels. So let's call a channel, or let's draw a channel as a resistor. So this is now a resistor or a conductance. You know that conductance and resistor is one over the other. So this is, let's say, the conductance of the sodium channels, which is the total conductance of all the sodium channels in this piece of membrane. This is the total conductance of all the sodium channels that will enable, if open, for sodium to fly through. This will be the outside of the cell, the outside of the membrane, and here it will be the inside of the membrane. And here I draw the battery. So this is now the battery, the Nernst potential for this ion. We know that it's about something on the order, as we said before, plus 60 millivolts. And so you can see that the large part, the longer part of the battery is directed towards the inside. This means that this battery is positive inside. And this is, as I said, the total conductance that will enable sodium currents to flow from out, in this case, to the inside of the cell. Let's look now at the potassium. So this is the total conductance of all ion channels for the potassium, and this will be now the potassium battery, or the Nernst potential for the potassium. This will be the Nernst potential for the potassium. You can see now that the negative part of the battery is directed towards the inside. This is now something like on the order of, as we said, something like 72 millivolts or something like that. And then there is the third one, which is the chloride conductance, G chloride, and there is also, this has to be negative. Okay, so the negative side of the chloride is directing inside. Okay, and I also want to add something that we did not discuss at all, and this is the membrane capacitance. Because we know from experiments also that there are these ion channels that enable current flow through the membrane, this direction and so forth, but there are much of the membrane is not channels, or much of the membrane does not allow charges to flow through, and it behaves like a capacitance. So it really accumulated charges inside versus outside. So this is now, what I drew now is actually a model of the membrane. This is the membrane. This is the outside of the membrane. This is the inside of the membrane. And between the outside and the inside, there is a voltage drop. There is some voltage, called it V membrane. So there is a difference between the outside and the inside, which is a combined weighted sum of this circuit. So this battery with this conductance contributes something to this membrane voltage, and this conductance and this battery contribute something, and so forth. And in order to describe the resting potential, which is the basic potential that the neuron sits on without any particular activity, neither synaptic nor spike, I will have to now describe to you, or actually solve for you, this circuit. So now I'm going to solve the circuit. But we made just intellectual jump now from a biological description of the membrane through Nernst equation, knowing that there are these three particular ions, into a circuit that could be written mathematically, because this is now an electrical circuit and we understand the mathematics of electrical circuits. So I can in principle now write the equation that describes this whole circuit. Okay, so now that we have this circuit, I would like now to write the equation for the circuit, and this comes from Kirchhoff law, and the Kirchhoff law will give me the description, mathematical description of this circuit. I just want to add one thing, that in what we call the resting potential of the neuron, so without any stimulation, without any excess activity, no synaptic activity, no spiking activity, the total current, so all the currents going inside and outside, the total current, which is actually the total membrane current, which is actually the sodium current plus the potassium current plus the chloride current, at steady state, at rest, without any voltage change, this all should be zero. So based on this equation, I'm writing now the conductance equation. So one thing we have to remember, that if I want to describe a current over this particular, let's say, sodium path, I'm doing the following. So I'm writing now the current for the sodium equation, for the sodium current, and this is here. So I sodium is actually G sodium multiply by V, which is the voltage drop across the membrane, minus the battery of this particular ion. So this is very simple to understand, because across this battery there is voltage, membrane voltage. So the difference between inside and outside, the voltage difference is here. And this voltage difference is multiplied by the conductance 1 over the resistance of this particular resistance for this, or conductance for this ion, and this will give you the current, the sodium current, that flows across this branch. This will be true for all the ions. So I could write another equation similar to that for the potassium and for the chloride, and because I want all the sum of all these equations to be zero, then I get, if you just do that and write INA like this and IK like this and so forth, and you sum them up and you equate them to zero, you will get that the resting potential, the voltage at rest without any stimulation, is equal to GNA multiplied by ENA plus GK multiplied by EK, the Nernst potential for the potassium, plus G chloride multiplied by E chloride, divided by GNA plus GK plus G chloride, which is in neurons typically something like minus 70 millivolts. So this is very interesting. What I just showed you, just using the numbers before that came from the Nernst equation, and using this equation here to describe current flow over one branch and then over another branch and over the third branch, assuming that these are the three currents, only the three ions that determine the voltage across the membrane. I now neglected completely the capacitance because there is no voltage change, so there is no capacitance current. Then I get this equation, which is called the conductance equation, which really describes the voltage across the membrane of a neuron at rest, the resting potential. Sometimes it is called E rest or V rest. And I just told you that it is minus 70 millivolts inside the cell. This means that at rest, without doing anything, before you get a spike, before you get a synaptic potential, just at rest, when all the currents balance each other and you get net current, so there is no voltage change, the inside of the cell is about 70 millivolts more negative compared to the outside of the cell. So neurons sit, because of these gradients of concentration of the 3 ions that I mentioned, neurons, all the neurons in the world, sits in a negative potential inside versus outside, and this is the reference potential for all the rest of the potentials, for all the rest of the electrical activity that I will speak about. So if I will speak about a spike, it will start from minus 70 and then jump to the positive direction. If I will speak about synaptic potential, they will start from minus 70. They could be more positive or more negative, but all relative to minus 70. So this minus 70, this resting potential, is really the baseline, the reference potential for all other development of other types of signals, the spikes and the synaptic potential. So this is really the essence of the electrical basis for neuronal activity. And maybe I will end by saying the following, this part I will end by saying the following, that the trick of neurons, really the trick of neurons, is to be able to change the conductances very fast. So if I could change the potassium conductance very fast, I will get a more negative potential inside because of this negativity here. If I will succeed to change the sodium conductance very fast, I will get a more positive voltage inside. And so that's the trick of neurons, the fast trick of neurons to change potentials, both synaptic and spiking, is by changing these conductances. But what makes these conductances change, that's the trick of the membrane of neurons, which is very unique. And this is, of course, the next thing to explain to you. What is the origin of the capability of the conductances of the membrane to change and thus generate new voltages, different voltages, the synaptic potentials and the spiking potentials. So let me summarize this introductory part to the electrical activity of neurons. I just said that the membrane ion channels are the pores, are the conductances when open that enable the flow of currents from the inside to the outside or from the outside to the inside across the membrane. And I told you that the 3 key ions that play a role in determining the potential of membranes, of biological membranes, of neuronal membrane, are the sodium, the potassium, and the chloride. There are other ions, for example, the calcium, but for the resting potential at least, these are the 3 most important ions. And what really makes this difference in concentration of ions enable to generate voltage is their capability to cross the membrane, and this gradient of voltage is captured by the Nernst equation as a battery. So I can speak about 3 batteries that determine the overall voltage at rest and also for other potentials. These are the ENA, the battery of the sodium, the Nernst potential for the sodium, the battery for the potassium, and the battery for the chloride. And I showed you in this conductance equation that overall you have some kind of a balance between the 3 batteries and their corresponding conductances. So the conductance of the branch that has the conductance of the sodium and its battery, the branch that has the potassium conductance and its battery, and the chloride conductance and the battery, the combined equation, which is the conductance equation, determines the end result of the resting potential. I showed you that the resting potential in a typical neuron is around minus 70 negative inside compared to the outside, which, by the way, means that the dominant conductance at rest is the potassium conductance and the chloride as well, but the potassium conductance really determines mostly the resting potential because it is the potassium conductance which is associated with a negative battery of the potassium is the one that is most dominant, meaning that at rest the sodium is not very conductive. Otherwise, its battery would influence the resting potential and it will be more positive. But because the sodium channels are closed at rest, the battery of the potassium is the dominant battery that determines the resting potential to a large extent. And also, we shall see later, and I just mentioned it at the end, that every electrical activity, at least the fast one, like the spike and the synaptic potentials, are the result of the changing of the conductances, these three conductances that I mentioned. A fast change in the conductance will change the balance of the batteries or the contribution of the different batteries. For example, if I enable a change of the sodium conductance, GNA, if it becomes big suddenly, much conductance, many ion channels are open for sodium, then its battery will become dominant and the resting potential will move positively to something more positive. And if the potassium channels are very, very, very dominant, then you will go more negative than the resting potential towards minus 80 or 82 or 85 of the potassium battery. So this is the game of neurons. In order to generate electrical activity, they will somehow find ways, and we shall talk about the two ways they do it, in order to generate the spike or to generate synaptic potentials, using conductance change of these three ions that we spoke about.